Okay, hello. Good morning, everyone. Welcome to today's SA2C TED chart on SymPy. I'm Channa. I'm going to carry on this TED chart. And before we go into the details, I would like to give you a brief outline of the chart today. First, we are going to see like what is symbolic computation and a brief introduction to SymPy and why you might want to use SymPy and what are the advantages of using SymPy and the relative disadvantages. Then we go into into the basics of symbols, like how to create symbols using SymPy and how to use them in carrying out mathematical operations. And we'll see like how to print in a pretty format instead of the default printing format that is provided by SymPy. And then we will look into expressions, how to manipulate expressions, and how to use these expressions as polynomials and find the roots of the polynomials. And towards the end of the TED chart, we will look into the basic calculus, like how to differentiate an expression, how to compute the limits, and then we will look into matrices, the basic linear algebra, for example, matrix additions, transpose, and if you want to solve a simple matrix system of equations, how to do that using SymPy. And at the end, if time permits, then I will also go into tensor calculus, and we have to see if how much of time we will have towards the end of this lecture. I'm thinking of showing you how to use SymPy using in an interactive Jupyter notebook, and I would like to limit the session to 40 to 45 minutes, and please stop me at any time if you have any queries, if you need any clarifications, and I would like to keep 10 to 15 minutes at the end for more questions if you have any. Okay. Uh, without further ado, let's go into using SymPy. Okay. I'm not going to show how to install SymPy. You can, if you want to use SymPy, then you can simply go to Python web pages and install SymPy. Okay, first of all, what is symbolic computation? Okay, symbolic computation is the task of computation of mathematical objects symbolically. What exactly does it mean? It means that we do not make any approximations with respect to mathematical objects. For example, if let's say we want to compute the square root of number 8. Okay, this we can do in many ways. For example, if you want to do it numerically, then we can import this mathematical package from Python and say, give me the square root of 8. Then we get some number. Okay, it is a floating point format. Please note that this is an approximation of square root of 8. This is not the exact value of square root of 8. This is only a floating point approximation. If you want to do this symbolically, then we use SymPy. For example, okay, we import the SymPy package and then say SymPy square root of 8. So the simplified expression for square root of 8 is 2 square root of 2. So this is the exact value of square root of 8. In this way, we perform symbolic computations by working on mathematical objects in their pure form without making any approximations about them. Another way of looking at this is we can check the type of the variable that we are performing or type of the output that we are getting. For example, if we say math dot square root of 8, then it shows us that the type of the output is floating point format. Whereas if you type SymPy of square root of 8, then we get a different different definition of the variable. Okay, so in this way we can actually differentiate what is symbolic computation and what is numerical computation. Okay, now what are the advantages of using symbolic computation as opposed to numerical computation that we are often used to? So using symbolic computation, we can work with mathematical objects in their pure form, that is without making any approximations. And we can work with we can use symbolic computations in the pilot studies. For example, if you want to test a model without before actually going into implementation on high performance computers and perform some large scale simulations, we are interested in testing whether the model works or find some limitations of the model before actually doing some extensive studies. In this way, symbolic computation is really helpful. That the disadvantages are the symbolic computation is quite expensive computationally when compared to numerical computations. So the scope is actually limited not only by the computational efficiency but also by the limitations of the mathematical analysis that we can perform. For example, if you are interested in finding the solutions of a differential equation, then we may not we may not achieve it in every case because the domain that we are interested may not have an analytical solution. So symbolic computation might not be useful for those applications. Now coming to SymPy, why might you want to use SymPy? What are, or rather putting it this way, what are the advantages of using SymPy? The first advantage is that you will expand your knowledge of Python. That's the first advantage. And the second advantage is that it is open source. So we are not limited by some some corporate license fees that we need to pay every year. We don't have to renew it every year. And another advantage of using SymPy is that we can use SymPy and customize it depending upon our needs. We can extend SymPy by taking the code, by modifying the code. You can customize it depending upon your application. So this is another advantage. Another advantage of using SymPy is that it is lightweight when compared to the software like Mathematica, Maple, or MATLAB. These three are the options if you are interested in symbolic computation, but their installation is quite complicated, although they have much more functionality when compared to SymPy. One advantages of using SymPy that I really like is its ability, the ability that we get. So if you want to teach online using Jupyter notebooks, it's straightforward to use. As I'm showing it here, it's straightforward to use SymPy. If you are interested in teaching some basic mathematics courses online, you can use SymPy and demonstrate some differentiation, integration, and so on using SymPy and Jupyter notebooks. It's very useful in that way. Okay, so this is the introduction. Okay, now let's delve into the details of symbolic computation using SymPy. If I want to do some mathematical operations, let's say I want to do some x times x plus 2. This is the expression I want to elaborate. I want to work with. What happens if I type enter? So it says name x is not defined. So you have to tell the Python environment that x is a symbol. So that is before using any symbol, we have to define it. The way to define it is like this. First import SymPy, and then we can define the variable. So this is how we we define variables in symbolic computation using SymPy. Then if I type x times x plus 2, then I don't get any error message. It gives me expression. Note that here it doesn't simplify or expand the expression that I type. It prints the expression in its given form. The reason being that the user might be interested in its current form, because, for example, if I might be, you might be interested in factorization. So if you want factorization, then you can use the associated function to factorize the given expression, that polynomial. Or if you want to expand a particular expression, you can use expand function that we will see in a few minutes. Okay, we can also define multiple symbols. In order to avoid typing SymPy every time, let me do this. I'm importing everything from SymPy. Okay, so now I can define multiple symbols at a time by using the syntax. Now I have defined 4 symbols, x, y, z, and t. I can use them however I want. So for example, I can say f equal to x times y times z plus t times x, whatever, some expression. And if I want to print f, I can either simply enter f and press enter, or I can say print f. Note that the output that you get from the print function is the string format. Python also provides some pretty printing functionality that we will see in a few minutes. But before that, I will try to focus on some very important aspects of symbolic computation. That is the definitions of the symbols. We have to be extremely careful when we define the symbols, because I can say that symbols equal to x equal to y. So it doesn't comply. In this case, x is actually y. So if you are not careful when you define your symbols, then you might make lots of mistakes, and it might lead to lots of confusion. So I caution you to be extra careful when you define your symbols. Now we can use the function expand if you are interested in expanding a certain expression. So okay, so here as you can see, x is actually y, because I define x equal to symbol y in line 18. So let me redefine x as x. So you can use expand to expand a certain expression in this way. And if you are interested in factorization, so you can use factor to get factors of the given expression. Okay, so in this way we can use symbolic computation to perform some basic mathematical operations on the expressions. We can also evaluate an expression for a given value of the variable. For example, let's define this. Let's define an expression like this, and then we can say expression dot substitute x equal to 1, then it evaluates the expression by substituting x with 1, and then gives the output. Okay. So far we have looked at a very simple expression, but if you are interested in integrals or differentiation, then it will be very really useful if you have some pretty printing format that available to us. So that we can achieve by activating what is called as uh, initiate printing. So this is a function that we should call if you want to get the pretty printing option available to us. So once I press enter, that functionality is available to me. Now what I can do, if I type this, you can see clearly that the output format has changed. Now instead of giving me the output as a string format, then it is showing me in a pretty format that we are accustomed to when using mathematical objects. This pretty printing will come really handy when you are working with integrals. So you can see the integral symbol and differentiate the derivatives and all of that. Okay. Another option that is available to us when we define symbols is we can specify whether a particular object is a symbol or a function, or whether it is an integer or not. For example, I can say x, y, and z are integers. In this way, we can limit the type of symbol to particular class of numerical values. I Similarly, I can define functions in this way. Symbols f, g, and then I say that class equal to function. Now here f and g are functions, whereas x, y, z are the symbols which are limited to integer values. We can cross check the type by typing the type of the function. Here it is an undefined function. If you type x, it shows a symbol. It shows that it is a symbol. So in this way, we can have we can differentiate one object from the other by naming by passing the appropriate input to symbols function. Okay, if you don't have any question, then I'll go ahead with the next topic. Next topic is the polynomials. We'll see how to work with polynomials in detail. For example, I have this expression. Let me define some polynomial. Okay, this is f. Okay, and I want to simplify this. I want to see if I can simplify, if I can factor out some common factors from the numerator and denominator and simplify this expression. If I want to do that, then I can use this command simplify. Now it factored out the factor x minus 1 from both the numerator and denominator and gave me the simplified expression. Often when we are working with polynomials, one thing that we often are interested in is finding the roots of the polynomial. find to see how we can find the roots of a polynomial, let me use this expression. Okay, so this is my f, and I want to find the roots of f. uh, if, for that I can use solve function. For solve function I have to pass the expression, and then I have to give the symbol for which I want to compute the solution. Okay, so now this solve function through the output as 1 comma 2. So as we can see, this polynomial has roots 1 and 2. So in this way we can use the solve function to find the roots of a polynomial. I'm going to show another example for finding the roots of a polynomial. This time I'm taking this expression, x squared plus x plus 1, and then I say solve g comma x. So yeah, so it didn't give me anything because this this polynomial doesn't have any roots that are real. If you modify the definitions for symbols, for example, if I say symbols and I don't pass any other arguments, and I redefine x, now you see, now it gave me the solution. The solution has complex roots. The solution has complex roots, right? Okay, so in this is another example that I picked because I wanted to show you what happens if you are not careful when defining the symbols. If you limit the definition of a symbol to particular data type, then you may not get any solution. And it is important that you understand the definitions of your symbols when you use them, because we expect that we should get some solution when we use this solve function to get the roots of the polynomial g at line 41, but it gave no output. If I didn't know that I defined x uh, by limiting it to integers, then I would be lost. If you have a polynomial that has say 100 tens of roots, then it may not be often advantageous. It may be confusing if you print the output directly to the screen. So what we can do is we can store the output of the solve function to a variable, say in this case y. uh, Before that, let me redefine y. Okay, now I know that y is of size 2 because this polynomial must have two roots. So I can say 1, it gives me the first root. Then if I say y of 1, it gives me the second root. There is another functionality that is available to us. Instead of printing it as rational numbers, we can ask it to evaluate it to numerical values using this evaluate function. So the output of this is in terms of floating point numbers. So this is how we can use SymPy to solve some simple polynomial equations. Uh, we can extend this functionality to solve a set of equations. For example, if you are interested in solving n equations in terms of n variables, then you can use this solve function in a similar fashion. For that, let me define the variables, the symbols xyz again, just to be safe. Okay, I now have xyz as variables. Then I'm going to define three equations in three variables xyz. So the syntax for defining an equation is like this. You have to use the function capital U, capital E, small q, and then you type the left hand side followed by comma, then followed by the right hand side. So the first equation is x plus y plus z equal to 0. And similarly, I define the other two equations. Okay, now I have defined the three equations, which I can now use using the solve function to find the solutions of this system of equations. So we have to input these three equations in the form of a list. So this is the list of three equations, and we need to say the variables that we want to solve for, and the variable list should also be in the form of list. So what this function represents here is that I am requesting solve function to solve the equation 1, 2, 3, and give me the output for x, y, and z. Okay, so once I solve this, now I get the values for x, y, z. In this way, you can use SymPy to solve the system of equations. Okay, I think I will limit the discussion or the presentation of polynomials uh, to this point, and then now I move on to basic calculus, like to show how we can use SymPy to perform some basic calculus operation, for example, differentiation and integration using SymPy. Okay. Okay. So to achieve this, let me define an expression, say x squared, f equal to x squared, and I want to find the derivative of f with respect to x. Then that is 2x. Similarly, I can compute the derivative of x n times by passing the third argument. For example, if I want to compute the derivative of x with respect to x one time, then I say 1 at the third argument, the result is the same. If I want to compute the derivative 2 times or 3, let's say 3 times, then I pass 3 at the third argument, then the result should be 0. Okay, I get 0. So in this way, we can use diff function to find the derivative of any expression with respect to a certain variable, and as many times as we are interested in. To learn more about this, let me define a more complicated expression. Sin x times cos y times exponential of z. This is the expression that I'm interested in, and I want to compute the derivative of g. with respect to z 2 times. Since the exponential of z with respect to z is exponential of z, then the output is the same as the input. In this way, I can perform differentiation with respect to any variable and as many times as I want. Now, what happens if I don't specify anything? If I say just diff g, if I say diff j, then it complies. So, the error actually is pretty useful, since it says since there is more than one variable in the expression, the variables of differentiation must be supplied. So when we are interested in performing the differentiation of a, a, an expression that consists of more than one variable, then we should specify the variable with which we want the differentiation. And if you don't specify the third argument, it will perform the differentiation once. And if you are interested in integration, we have to use the function integrate. Here I want to evaluate the integral of f with respect to x. Now this integral is going to be x cubed by 3. I do not understand why they have used the short form for differentiation and then the long form for integration. I don't know the reason behind it, but this is one thing we have to keep in mind. This is the name of the function that we have to get familiar with when we use SymPy. Diff is for differentiation, whereas integrate, the whole name we have to use for performing integration of an expression. This is performing the operations in place. We can, instead of performing the operations in place, we can also define the operations first and then perform them later. For example, I say derivative of f with respect to x and then with respect to z and then with respect to t. So if I type df, then I can say the derivative printed in its pure form, like with respect d cube, first with respect to x and then with respect to z and then with respect to t, and then it shows the function f is equal to x squared. It shows the function. So here I have defined the derivative. Then after this I can perform the derivative by using this syntax df dot do it. Now it has computed the derivative. The derivative is 0 because f is only a function of x, and the derivative of x squared with respect to z or t is 0. Here one problem I had, maybe it could be a potential issue when you are using SymPy, and that I need to get clarification from SymPy, is the symbols. Here I'm defining the derivative, and I want here, as per my understanding of mathematics, d stands for the pure derivative, whereas dou stands for the partial derivative. So I'm assuming that this do it is performing the partial derivative rather than the pure derivative. So this we should get a clarification from SymPy. What exactly do they mean when they type d instead of do? But this is one thing you should be aware of. When we ask for a derivative, SymPy actually performs a partial derivative. Okay, if you are interested in finding the limits of an expression, for example, I want to find the limit of sin x by x as x goes to 0. So this is the expression. First, I want to specify the function. Function is the first argument, then the variable, and then the limit value. This 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 line evaluates the limit of sin x by x as x goes to 0. So it says limits is not defined. Okay. To use this, I think I need to import everything from SymPy. Oh, I apologize. The syntax is limit, not limits. Okay. So now the limit of sin x over x when x goes to 0 is 1. So we got the correct answer. We also have functionality to find the Taylor series expansion of a particular expression. For example, let's say I'm interested in the Taylor series expansion of the exponential function. F is the exponential of x, and I want to expand this f in terms of Taylor series. So the syntax is f dot series, and then the variable is x, and then about 0, and then I'm interested in the first four values in the series. So this is the Taylor series expansion of exponential function in x, and here it will also show you the higher order term. We can keep it or we can remove it by using this syntax. For example, if I'm not in, if I want to remove that o from the output, I can say remove bit o. So when I do that, then it doesn't show bit o in the output. Using this series function, we can find the Taylor series expansion of any expression that we are interested in. For example, if I want to find the expression about 2 about 2 instead of 0, then I type like this. Here I want to find the Taylor series expansion for f at 2, and I'm interested in first 4 values, and I want to remove the bit o expression from the output, and then I type this. Okay, so this is the Taylor series expansion of the exponential function about 2. Okay, next we go to matrices and some basic linear algebra. The syntax for defining a matrix in SymPy is matrix, and then we have to specify the input as a list. So if I say this matrix of 1 2 3 in square brackets, then here I am defining a matrix with input 1 2 3, and then I'm storing it in A. When I say A and print it, it shows here I'm defining a column vector that which is a matrix with one column. Here A is a column matrix. In this way, I can define another type of matrices. If you want to define matrices with multiple rows and columns, then you have to specify them as a list of lists. So now I have B as a square matrix. So in this way, we can use SymPy's functionality for matrices. Once we define matrices, we can perform various operations of them. For example, if you are interested in finding the transpose, then I say B dot capital T, that gives me the transpose of B, and we can multiply the matrix with some number, and then add two matrices. So these are the basic algebraic operations that we can perform on matrices. And more often than not, we are also interested in finding the eigenvalues and eigenvectors for matrix. If you are interested in that, then we can find the eigenvalues of a matrix by using the eigenvalues function. Sorry, yeah, eigenvalues, not values. So this d dot eigenvalues, it gives us the eigenvalues of matrix D, and we can also find the diagonalization for a particular matrix by using this. Say diagonalize E is the diagonal matrix, and P is the matrix of the eigenvectors. Okay, and we can also get characteristic polynomials of a matrix by using this expression, by using the function char poly. For example, I want to get a characteristic polynomial for matrix D, but before I do that, I have to define a symbol. Let's say I want to get the characteristic polynomials in terms of lambdas. Now I say polynomial P equal to D dot char poly now P is a characteristic polynomial of D, and it also specifies the domain of domain for lambda. In this way, we can use we can do symbolic computation in SymPy by defining polynomials, matrices, etc. Okay, since we are running out of time, I need to rush. Okay, so this is so far what I wanted to cover on the basic functionality of SymPy for performing symbolic computations in SymPy. Okay, if you have any questions, then please ask.